actually got to finish off one more reaction from chapter 9, and then we're done with all our new content. So we'll spend the rest of the period reviewing chapter 9 material. Remember these ones, where was it? We last left off with these aldol addition reactions that take place between aldehydes and ketones, where you're forming a new bond between the alpha carbon of one and the carbonyl carbon of the other. All right, so let's practice this again real quick. Do a very simple aldehyde here so it's not so ugly. All right. This is what happens when you add a little base to a sample of your aldehyde or ketone. So again, take a second to draw me the product, and what we're going to be doing is connecting the alpha carbon of one to the carbonyl carbon of its neighbor. All right, so we said the easiest way to do this was to start by actually redrawing your aldehyde or ketone from your enolate, the one where the alpha carbon's going to be doing the attacking. And then you can draw in your other two carbons, make your new bond. All right, and that carbonyl oxygen on that carbonyl carbon goes from being carbonyl to what kind of functional group? Yeah, so it goes from being a carbon-oxygen double bond to just a carbon-oxygen single bond. So we can double check our work here. Same way we can always double check, first of all, just count carbons, right? We should have the same number of carbons on either side. Check your connection. Make sure your alpha carbon from one, that's the one right next door to the carbonyl carbon, is connected to the carbonyl carbon of the other. Check, check. And then there was one other way that we can use to double check these particular products, and this is going to be especially helpful for when we start working backwards to predict our reactants, and that's making sure we have this 3 carbon spacing. So I start counting at the carbonyl carbon. My 2 oxygens are 3 carbons apart from one another. All right, so that's an easy way to sort of double check that your structure makes sense. Let's do one more with something uglier. I am. All right, so again, I'm going to be attaching the alpha carbon of one to to the carbonyl carbon of its neighbor. That's where my new bond should be between those two carbons. Start by redrawing this one. The one with the alpha carbon that's going to be doing the attaching, because that functional group doesn't get disturbed. Now I need to draw a new bond to what was the carbonyl carbon of my other molecule. All right, now I'm going to have to make sure that all my connections are correct here. So this guy has these on either side, and there should be an alcohol group there. It's kind of ugly. All right, and this is just sort of by virtue of the number of bonds that you end up drawing, but you can see that when you start with aldehydes, it's a little bit neater looking than when you start with the ketone, because when you start with the ketone, you're going to be creating this tertiary alcohol, right? So you just have this really crowded center right here, but nonetheless, this is all correct here. Again, I can double check by counting carbons. Should have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all right. I can double check that my connection's correct. I got my carbonyl carbon, my alpha carbon connected, and then again, for this particular reaction, I should have this 1, 2, 3 carbon spacing. All right, and again, that 3 carbon spacing is going to be really helpful for when we work backwards.
How do you decide which one is the alpha carbon?
The alpha carbon is the one located right next door to the carbonyl carbon, so it's always 1 carbon away.
So if I had used the other carbon?
If you had used this one right here,
Yeah.
you would have gotten the same thing.
Okay.
Just like flipped upside down like a pancake.
Okay.
Both of those are alpha carbons, yes. Okay, so these are what are called aldol addition reactions. The one that we haven't gotten to, the last of our reactions that we're going to have to learn, very similar, called an aldol condensation. And this is the sort of exact same thing, but instead of just having sodium hydroxide, you have sodium hydroxide and heat. Okay, and I'm going to start with my aldol addition product and then show you how we get the condensation product. This is essentially an aldol addition followed by a dehydration. We're going to turn this alcohol group into an alkene, into a double bond. Okay? So what's going to happen is notice that I've colored my 2 carbons where this new bond is formed. All right, so everybody take a second and just look up on the board and watch me do this. I'm going to convert this aldol. I'm going to get rid of this OH group and turn it into a double bond. All right, so the condensation product, when you have sodium hydroxide and heat, you get, instead of an alcohol group, you get a double bond formed between carbons 2 and 3. All right, so again, our counting is going to be really helpful in figuring out what's going on here. Take a second and see if you can't convert this addition product into the condensation product.
Does it go to the more substituted carbon?
No, it's always going to go between carbons 2 and 3. Right, so once you when you do your aldol addition, you can do your counting and you should have these 3 carbon spacing between your oxygens. That double bond's always going to go between carbon 2 and 3. So again, instead of having this alcohol group on carbon 3, I'm going to get rid of that and replace it with a double bond between carbons 2 and 3. so congratulations, you're done with all the reactions that we're going to cover in this course. All right, we are going to practice one thing before starting the review. Well, I guess it is review, but nonetheless. And that is just working backwards. If we are given an aldol, how do we figure out what our reactants were? Okay, and again, the key to life here is going to be that 3 carbon spacing. I'm going to start counting at my carbonyl carbon and then move towards the other oxygen. I have that perfect 3 carbon spacing. Importantly, this will help me identify which bond was formed in this reaction. All right, let's take a look back at the example that we just did. In both of these reactions, our new carbon-carbon bond is between the same 2 carbons. Which 2 carbons? 2 and 3, right? So between carbons 2 and 3, I have my new bond. So same thing over here. Right off the bat, I can identify that this is the bond formed in this reaction. Okay? Importantly, the one that has the alcohol group on it, this must have been my carbonyl carbon, right? Because when that new bond formed with the carbonyl carbon, that double bond became a single bond with the oxygen. And the other one, this is going to be my alpha carbon where that bond is formed, right? So if I'm going to figure out what my reactants are, I'm going to get rid of that bond. Right, break that bond that was formed in that reaction. And then importantly, I got to turn this alcohol into a carbon-oxygen double bond. So those would be my 2 reactants. All right, so if you're working backwards, you just need to look for that 3 carbon spacing of those 2 oxygens. Again, start counting at the carbonyl carbon, the carbon-oxygen double bond. All right, so we sort of had this little strategy last time. Let's just finish this off because I start counting at that carbonyl in the product. New carbon is always between carbons 2 and 3, and I guess the last thing is convert the OH to a carbonyl.
This is with NaOH and heat?
This one would just be with NaOH. The other one, if it's heat, it would have a double bond instead of an alcohol. And we'll work on working backwards for that when we do our review. All right, so again, we're going to focus on chapter 9. Let's rewind all the way back to the very beginning of the chapter, where the first thing we would have been doing would be nomenclature. All right, so maybe let's focus on doing a few of these, and then I'll post this with the answer key so we can, I don't want to spend too much time copying down all these individual problems. So let's focus on a few of them so we can make sure to touch on all the different aspects of the chapter here. So let's do these 3. let's do this very first one together. It's probably the easier one up here. I have 1, 2, 3, 4 carbons. So what prefix is that? What do I use for 4? Bute. And so this is butanal. The al is how we refer to aldehydes. All right. Remember, the other weird thing with aldehydes is you actually don't have to put the number of where that functional group is. Since it's always on the end, we say that this is always carbon 1. So we don't bother writing 1-butanal, we just say butanal. Okay, but remember that carbonyl carbon is always carbon 1 when you're numbering. If I do the one right below it, this is a ketone now. It's 5 carbons, so 5 carbons is pent. This would be pent unknown. One is how we refer to our ketones. For ketones, you do need to make sure to include the location of that functional group. So in this case, this would be 3-pentanone. All right, so again, see if you can't do, given those 2 that we just worked on, see if you can't do, I don't remember which ones I circled now. Those 2. Oh no, I guess it was this one. Okay, 5 carbons we said was pent, so pent now. Importantly, when you're numbering this one, the key is you need to make sure that you start at that carbonyl carbon. All right, so this would be 4-fluoropentanal. All right, this last one here, which is not one of the ones that I told you to do, but let's just do it together real quick because it illustrates a really important point about nomenclature. I have 6 carbons, so this is a hexanal. Now I have 2 substituents here. I have this 2-carbon group, which we call an ethyl group. And I have this 1-carbon group, which we call a methyl group. I'm going to start counting. 1, 2, 3, 4, 5, 6. So the ethyl group is on carbon 3, and the methyl group is on carbon 5. Importantly, when I go to assemble the name, I'm going to put these substituents in alphabetical order. Right? So the ethyl has to be listed before the methyl. 3-ethyl, 5. I'm not going to have enough room. Methyl. Right, so this is only really a situation that arises when you have more than one substituent, but when you have more than one substituent, you got to make sure to list them alphabetically when you assemble the name. All right, and we said we were going to do this one here. I can see my parent chain is going to be these 1, 2, 3, 4, 5, 6 carbons. So I got a hexanone, right, because this is a ketone, not an aldehyde. So hexanone. Then I'm going to do my numbering. I can sort of do it two ways. If I'm having trouble seeing which way it should be, I can just always do it twice. 1, 2, 3, 4, 5, 6. Remember, for these functional groups here, you're going to prioritize that ketone functional group. So I'm not even going to pay attention to the chlorines. I'm going to pick the numbering scheme that puts that ketone functional group on the lowest possible carbon. So in this case, that would be the blue numbering scheme. All right. So that's a 3-hexanone. That's where that own functional group is. And then how do I account for those chlorines? So, right, so this is a specific example I did just to drive a point home. You need to make sure to include 2,2, right? Anytime it's di anything, you should have both numbers in the name, even if they're both on the same carbon, right? This was 2,2-dichloro. Could have been 1,2-dichloro or 2,5-dichloro. You have to put both numbers in there, even when they're on the same carbon. So 2,2-dichloro, 3-hexanone. All right, and so then for the other one now, when we're doing the going to the structure, these tend to be a little bit easier. So I'm gonna my approach is to look at the back end first, right? First thing I'm gonna do is draw that parent chain with that aldehyde functional group. 6, 7, an aldehyde on the end. Now 1, 2, I gotta make sure to start counting from that aldehyde. 2,2-dimethyl. Heptanal. What's acetone? How many carbons? 3, right? So acetone is that simplest ketone. What about cyclohexanone? What do you think that's going to look like? A ring, right? Cyclohex. We know we got to draw one of our favorite shapes, the hexagon, and then the anone implies we have which functional group? So yeah, this would be a ketone, right? So this is just a ketone sticking off of a ring. Similar to aldehydes, we don't bother numbering it because no matter where we put it on that ring, we would just call that carbon 1. All right, and then I guess just to fill in real quick, this was all right. One of the other skills, and this is kind of odd for ketones and aldehydes that we've talked about, was drawing their corresponding enol and enolate ions. Okay, so take a second and see if you can't remember how to draw the enol and then the two resonance structures of the enolate ion. All right, so let's take a second and pick this apart. Enol. What do we think the OL, all, would stand for? Alcohol. And what do the ene mean in organic chemistry? Alkenes, double bonds, right? So that's exactly correct. This is going to be a molecule. We have the same 5 carbons, but now we're going to have a double bond located right next door to an alcohol group. That's what an enol is. Remember, this is like this reorganization within this ketone that happens where this hydrogen from the alpha carbon, carbon right next door to the carbonyl carbon, is going to jump up to form an alcohol, and I'm going to get a double bond between what was formerly the carbonyl carbon and the alpha carbon. That is my enol.
Isn't there like a minus group?
That's the enolate. The enol is neutral. All right, so yes, so these explain the reactivity of these particular molecules, ketones and aldehydes, in those aldol addition type reactions. That's why they were sort of introduced. To get the enolate, this is when you remove that alpha hydrogen and it leaves behind a pair of electrons. Right, so this little upside down smiley face thing, this is a negative charge on this carbon. This carbon has a lone pair and a negative charge now. All right, and this was one resonance structure that was stabilizing this negative charge. The other one I would get when this pair of electrons comes down here to form a double bond, kicking this pair up onto that oxygen. All right, so what I mean by that is now I have a double bond here, and the negative charge is on that oxygen. That can be good in drawing lone pairs. Okay, these are my 2 resonance structures for my enolate ion and the enol for this particular ketone, 3-pentanone. All right, and we had a good number of reactions that we learned for this particular chapter. So take a minute and complete this reaction web here for this aldehyde, butanal. Yeah, you will. So these are a little bit more difficult than they may be. All right, so let's start with this one here, the Grignard. This is one that we've done quite a bit now. We introduced it last chapter, we talked about it again this chapter. We want to make a little note that not only should we be able to go forwards, we should also be able to go backwards for these as well and predict reactants. Okay, so this particular one is asking for the product, but given the product of a Grignard reaction, you also need to be able to work backwards and tell me what two reactants you would use to create it. Okay. What's the functional group that we have in our product for Grignards? Alcohols, yep. That MGBR thing is our reagent, right? The functional group on our product is an alcohol. And importantly, what's going to happen is I'm going to form a new bond between the carbon attached to that magnesium and my carbonyl carbon. Okay, so I'm going to start by redrawing my aldehyde or ketone. Here's this one here. And now, instead of being a carbon-oxygen double bond, again, the functional group I should have here should be an alcohol. That carbonyl oxygen is converted to an alcohol. And I'm going to attach my 1, 2 carbons from my Grignard. All right, and again, these are Grignard reactions, just so you can sort of know where to look to practice them. This PPH3 business, these are Wittig reactions. I'm again forming a new bond between my carbonyl carbon that I highlighted in green and my carbon attached to the phosphorus. The difference here with the Wittig is that oxygen gets completely replaced. You're creating a new carbon-carbon double bond. All right, so if I start out with my 4 carbons from my aldehyde, I'm going to, this was formerly my carbonyl carbon, I'm going to now have a carbon-carbon double bond. Oh, you know what? I messed it up. It's CH2. Sorry. All right, so these Wittigs form carbon-carbon double bonds. You basically, you completely replace that carbonyl oxygen with what's on the back half of your Wittig reagent. All right, and when you see chromium, you think oxidation. Awesome. Remember, oxidation in organic chemistry is just simply creating more carbon-oxygen bonds. So oxidation of an aldehyde will create what kind of functional group? All right, you definitely want to know the name of it. Yeah, so this would be a carboxylic acid.
Why are you saying it?
All right, I've created an additional carbon-oxygen bond. So again, this would be oxidation. All right, and similarly, we can convert between alcohols and aldehydes using these oxidation, and what's the other one, the corresponding one? Kind of the opposite? Reduction, right? So using these oxidation-reduction reactions. Aldehydes can be reduced to alcohols, and alcohols can be oxidized to aldehydes.
That one's a weak oxidizer, right?
This one would have to be the weak oxidizer, exactly. I can't just use my chromium-based reagent anymore. I got to use one of the special ones. Again, you'll have a bank of all the different reagents, but you know, if you can come up with it off the top of your head, that's not bad. All right, this would be PCC or DMP. Either one of those are our two weak oxidizers. And what's our reducing agent? Yeah. Lithium something. Lithium aluminum hydride. LiAlH4. Okay?
So it oxidizes to an aldehyde for here, but if it was going to oxidize to a ketone, it would be
You would have to start with a different alcohol.
secondary or something?
Yeah, you'd have to start with a secondary alcohol. Which, speaking of, so basically you want to be able to do the exact same thing no matter what aldehyde or ketone I put in the middle here, right? So here is just the same set of reactions, but with a different, this time, a ketone in there. What's up?
Will the lithium also completely reduce the strongly oxidized?
So we haven't actually learned about it, but yes, actually lithium, like you could use lithium aluminum hydride to convert a carboxylic acid to an alcohol. I believe that's more or less what you were asking.
Yes.
Right, yeah, we actually didn't learn that, but you could. All right, so again, the same set of reactions, just with the ketone in here. We're gonna quickly go through this. You guys can copy down this, but again, it's the same set of reactions. I wanna move on to practicing the aldol additions because I feel like those are the scariest part of the chapter. I do wanna make a note about this one right here. What would be the product of oxidation of my oxidation of my ketone? No reaction, right? I can't further oxidize a ketone. So this is no reaction. All right, the rest of these you should be able to fill in. Again, really, you want to be able to put anything in the middle of there and tell me what those products are. I guess another point that I would like to make is that for the Wittig reactions, as well as the Grignards, I should be able to put any R group on there and you'll be able to tell me what the product was, right? I chose a specific one for these reactions. Should be able to put anything there. All right, and for my Grignard, if I just want to do it out, that would be OH. There's my R. And for the Wittig, it's going to be double bonded to that R. All right, I could put something big and ugly and scary there, like a benzene or something like that. Doesn't matter, it's still the same logic in terms of how it gets connected. All right, so let's do these. Let's do,
Could you put that fill?
I'm gonna post this document on Canvas, so with all the answer keys. So let's do a select ones here. Let's do this one and this one. sake of time, I'm going to start going through these. The key here is you need to be able to see which two carbons are going to be connected, right? If you know where your new bond is going to be formed, you should be good to go in terms of drawing your product. Remember, for these, it's going to be the alpha carbon of one and the carbonyl carbon of its neighbor. All right, so that should be my new bond there. My carbonyl carbon needs to be connected to the, my alpha carbon needs to be connected to the carbonyl carbon of my new molecule, or of my next molecule. Okay, I can double check by counting carbons. 1, 2, 3, 4, 1, 2, 3, 4 from that fragment. 5, 6, 7, 8, 5, 6, 7, 8. I got the correct two carbons connected to one another. And I have this 1, 2, 3 carbon spacing of my two oxygens. Right? Check your spacing of your oxygens. Same thing on this side. It should be the alpha carbon of one connected to the carbonyl carbon of its neighbor. So here's my alpha carbon I'm going to connect. So I'm going to color that. I'm going to draw the bond, the new bond that was created in this reaction. This then has to be the carbonyl carbon. I'm going to draw in the rest. Pretty gross pentagon, but that works. If this was the aldol addition reaction, there would be an OH group there. But because I have this heat down here, this was the last reaction that we learned today, this is going to create a carbon-carbon double bond between carbons 2 and 3, between my green and blue carbons. All right, again, I can count my carbons, 1, 2, 3, 4, 5 from this fragment. 1, 2, 3, 4, 5 from this fragment. All right, I got my connection. And that 1, 2, 3 carbon spacing, where now I have a double bond between carbons 2 and 3. All right, so in both of these reactions, that bond between carbons 2 and 3 were created in the reaction. If it's just NaOH all by itself, there will be an OH group on carbon 3. And if there's NaOH plus heat, there will be a double bond between carbons 2 and 3. Okay? Again, count your carbons. Check to make sure you've connected the correct two carbons, and then count your spacing of your oxygens. It's really easy to mess up the spacing of the oxygens. Your oxygens should be 3 carbons apart. All right, and then the last one, if we're going to work backwards, we have to be able to identify where our new bond was. Again, we're going to start counting. And this new bond was between carbons 2 and 3. So if I break this bond, that will give me my 1 fragment. And then what am I going to have to do to this alcohol group? Double bond, right? So boom, get rid of that hydrogen. All right, so I will work through the rest of these that we didn't get to and post this answer key for you guys to study on campus. All right, along with another one that will have different problems on there for you to practice. All right, next time we'll start reviewing one of the other chapters from this unit, it's the alcohols chapter. Later.
Thank you.
Bye, have a good one.